So, once that starts, what is a polynomial? Polynomials are what we've done in the past. In grade 11, we looked at linear graphs, so just lines, right? That's a polynomial. We looked at slanted lines, and then we looked at horizontal lines, which is a constant function. So what is a polynomial? Well, a polynomial could be like, okay, join me. Y equals 6. We're writing this down, we're paying attention. Because why am I putting rationals and polynomials together? Because if you pay attention in polynomials and try really hard in polynomials I feel like is one of the easier units. So I buffer the two units together, right? So if you don't try in polynomials, and if you think rationals is easy, cool, then you can just excel in both. But we're going to continually still practice rationals along the way, but we're also going to do polynomials. So pay attention and you can do this one really, really well. Now, polynomial, y equals 6. So what does that look like? If I had a graph, I picked a thin one, but that didn't do anything, did it? It's still the same. What's the point? Okay, cool. Y equals 6. She can be aggressively thick. That's fine. 1, 2, 3, 4, 5, 6. That would be what a y equals 6 looks like, right? It's a horizontal line. Now, it actually does have a variable. This equation has a variable. You just might not see it. Okay? It has a variable. Its variable is x to the what if it doesn't exist? 0. So actually constant functions are x to the 0. They just won't say that x to the 0. Do you see that though? So this y equals 6. So these are exactly the same. These two equations are exactly the same. Because y equals 6 is x to the 0. Okay? So they're called constant functions. You can put it down here if we'd like. It's the same as y equals 6 x to the 0, right? So my exponent is a 0, correct? So for a constant function, your exponent on the x is 0. Right? So we learned about constant functions. We also learned about linear functions. Okay? So in grade 10, we learned, okay, well, we could have y equals 3x plus 7. We agree? Now, what are the exponents on our variables? What's the exponent on this variable? X to the what? 1. And this one is x to the 0. So we still have whole number exponents, correct? 0, 1. And this is a linear. I have no idea what it is trying to do right now. Okay. It's the first time trying this computer with this, and it's going really well. Swimmingly, one might say. All right. Then in grade 11, we learned about these. 2x squared plus 3x minus 1. What were they called? Didn't matter if you were in 20-2 or 20-1, we talked about these. Nope. Quadratic. We're doing exponentials in the next unit. So let's check our exponents. Our exponents have to be whole numbers, correct? So this one is a 2. That's a whole number. Remember, whole numbers start with the number with a whole, and then your natural numbers. 1, 2, 3, 4, 5, 6, right? So 2, this is a 1. This is x to the 0. So we're still good, correct? That's why quadratic is still a polynomial. Okay, we do one extra in grade 12. It's called the cubic. So it's y equals, say, negative 3x cubed plus 4x squared minus 6x plus 1. So why do I think this unit should be easy? Because everything but the cubic function you have done. It should be completely a repeat. So this is 3, 2, 1, and then x to the 0. Now this is called a cubic. So what is a polynomial? Whole number exponents. I have no idea what is the 10th. Like, okay. Let's see what it wants to do. Let's try it out. Why does that exist? You don't let me. Okay. I have no idea why that is. All right. What is not a polynomial? Well, if whole number exponents are a polynomial, anything that is not a whole number exponent. So one example could be y equals 3 over x. What is the exponent currently on my x? Someone whispered it. It's a 1. Oh my goodness. It's a 1. But is it in the numerator? No. If I move it up here, what happens when you move something up? Every positive exponent becomes negative, every negative exponent becomes positive, correct? So this x to the 1, when I move it up, is going to become x to the negative 1. Is that a whole number? No, it's an integer. So it's done. So that is not a polynomial. Another one that is not a polynomial is y equals the square root of 3x. In grade 10, you talked about these, converting radicals, bless you, to exponents, to rational exponents. So you took your index, which is a 2, you took your exponent on it, which is a 1, and you dropped your index underneath. So we can rewrite this as y equals 3x to the 1 over, and drop our index underneath, 2. Is a half a whole number?
No.
No, so that's why it doesn't work. The one that is actually a polynomial that people mess up is they think this isn't a polynomial, but it actually is. So I'm going to draw it here. Y equals root 2 x squared. It is a polynomial. People think it's not because of the square root. Square root of 2 is just a decimal coefficient, correct? We can have decimal coefficients. What's our rule for it to be a polynomial? Our exponents have to be whole numbers. Is this one a whole number? Is 2 a whole number? Yep. So it is a polynomial. Okay. So that's what is and what isn't. All right. Next page. So we're going to look at linear functions. So these are, in grade 10, you guys call them mx plus b. In grade 12, you do like ax plus b. Oh, this is someone. I did you wrote a test yesterday and left it along on the side. Anyway? Ah, there we go. Like someone's binder. Okay, so we have ax plus b. All right. Not straight. He used a straight thing and didn't make straight.
It's not click on the thing and then right while it's open. So.
Oh, when I do this, and then I do this, and then I start writing, it closes. Ah!
Oh, thank you.
No, triple Venn diagrams may not be your thing, but that.
Yeah.
Yeah. And guess what's better in life to have? Genuine knowledge on a computer. Because when have you used a 3-Venn diagram in your life?
Right.
Never. Exactly. I mean, 3-Venn diagram is super important in your curriculum. I actually like 3-Venn diagrams. They're like a little puzzle. You know, geometry Venn diagrams are like a little puzzle. Okay. It doesn't matter. Rhyme or reason, just okay. So I want you to draw this. So I'm going up 2 over 1, up 2 over 1, and then I can go the complete opposite, down 2, left 1, down 2, left 1, and I have myself a line. Pretend that that's straight. I hope yours is. Mine, it's kind of hard to do on a board. So my equation is this. Y equals, because I went up 2 over 1, my slope is up 2, right 1, so it's 2 over 1, because I rise before I run. And slope, always think of it as rising before you run. Try and think of yourself getting out of bed in the morning. Do you rise before you run, or do you run before you rise? If you run before you rise, you are foolish. You are just given her in bed. Maybe you're sleeping. I don't know what you're doing. You're just like running. So when we get up and keep on with our day, we have to rise before we run, right? If we're late. Same thing with slope. You have to rise before you run. So this one is 2 over 1, but I can just write it as 2x. And then my last term is always my y-intercept, which in this case is minus 1. Wow, I'm so glad we figured out how to make that, as we figured that out. I mean, you figured it out, and I'm going to pretend now that I figured it out. Teamwork.
Yeah,
Mainly just you, but that's okay. Okay. So, what is the leading coefficient? The leading coefficient is the number in front. It leads the equation. It's the leading coefficient is the number in front, and leading means it leads it. Number in front of the largest exponent. So what is the leading coefficient of this one, of this equation? The number in front of the largest exponents. What's our leading coefficient? The 2. What is the y-intercept of this one? -1. We can pick it from the graph, but also the equation as well, right? So how do we get our y-intercept from the equation? I'm going to write it up here. The y-intercept is the constant term and the constant term is the term without a variable. If the equation doesn't have brackets. So as long as your equation doesn't have brackets, the term without the variable is the constant term, which is also your y-intercept. Very important. So here it's this one, right? And we write our y-intercept as a coordinate. What is the coordinate of a y-intercept? What's my x of the y-intercept always?
0.
0, comma, -1. How many x-intercepts does this one have? Because this says number of x-intercepts. It doesn't say the x-intercept, right? So it's just the number. So there's 1. Does a linear ever have more than 1? Does it ever have less than 1? No, it has to cross through at some point. At some point. I just said point. Yep. It has to cross through at some point. Not this point. Okay? What's the domain of lines that go like this? What are my x values? Or they go like this? This goes this way forever. This goes this way forever. In interval notation, which we're not allowed to use in 30-2. What's it called? X is a, no, no, not you. X is element of the reals is great. You, who threw paper at him, whichever one of you did it. Your answer was not one. I like how you thought that was you. I don't think I've ever gotten annoyed with you, nor would I ever. These two on there, watching you. You ever like, wow, Mrs. Lepp's mad at me. Just think, no, she can't be, because she would never be. I'm Jaden. I rock. Right? Thank you. Now. But yes, you're completely correct. X is an element of the reals. Good job. Back to this. So we do this. You see how I have a squiggly bracket? You have to have a squiggly bracket, because the squiggly bracket means the set of. Now your squiggly bracket might look like that. That's okay. No one's judging you on your squiggly bracket. However, your squiggly bracket can't look like that, because that's not a squiggly bracket. Your squiggly bracket can't look like that. That's not a squiggly bracket. Okay? The squiggly bracket means the set of, so you have to have it. You can't make up your own bracket. In mathematics, that's actually what it means. It has a meaning. So it's the set of x values. Now, if we were doing a word problem, you guys, we've done word problems before in grade 10 and 11. And if we were doing a word problem and there happened to be a t instead of the x, we would use t such that, because it shows you what variable is in the question. I gave you an x as the x, right? So we use x. You will change that. If it's a t, this has to become a t. If you were in 20-1, you learned integral notation. I'm going to give you a golf clap. You can't use it in 30-2. It's not allowed. But I'm glad you learned it. It was a good learning experience. Okay. Okay. Right, carry on. You can't use integral notation. So you have to use set. So the squiggly bracket x such that x is an element of the reals. Now, if you so much so didn't want to do the double line on the R, but you did a capital R without a double line, you're still right. No one's going to like take the marks off you and be like, ooh, no double line. Okay? But the double line is actually correct mathematics. Now we're discoing. With linears, we disco. Yep. Sure. We disco. You were in the middle of my disco. What? I don't believe you. Your face says.
Is it like?
There we are.
Is it gonna be? Is domain not every time?
It is for polynomial graphs.
Sorry.
Contain yourself. It is for polynomial graphs, but not if they're word problems. Because if you think about it, say the word problem is someone throwing a ball, time can't be negative. So if time starts at 0, so it would have to be greater. Okay. So, range. We're going like this again. We're discoing. So many phones out. So little time. I'm super important. Trust me. So full of information. Just oodles of information. So if I'm doing this, what does this mean for range? I go on for ever. So if ever you're discoing, it's X, E, R, Y, E, R.
That's why I do the arrows, right?
Yeah, that's what I'm doing. These are my arrows. Look at them. Yeah. Mm-hmm.
Can you back to disco for us?
This is me discoing. This is as good as it gets. I am not from the times of disco. I was born in the 80s. Don't make me older than I am. I'm old enough. All right. Y such that Y is an element of the reals. I don't even want to know. All right, so I'm going to give you another one. Okay. All right, so we have arrows here. Then we're going to go down 3, right 1, down 3, right 1. So let's come up with what the equation would be. Y equals, for linears by slope. What did I do? I rose, that's a rise or run, I rose down 3, right? Then I ran positive 1, correct? So it would be negative 3 over 1 for my slope. X And then what do I put at the back for the constant? What do I put at the back for the constant? What is it? 3. So I put a plus 3 at the back, because this is my y-intercept. And I can just rewrite it without the 1 on the bottom, because I don't need it. I will give you 1 minute to answer those 5. So what's my leading coefficient of this one? What's my leading coefficient? Yeah. So it's just -3 or -3 over 1. Stop. Then what's my y-intercept at? 0, 3. How many x-intercepts? Domain? X such that x is now in the reals. And y such that y is now in the reals. Now I'm going to give you guys a little bit of information. Your leading coefficient tells you how it ends on the right. So we're going to write this up here. Leading coefficient and this works for every polynomial. If the leading coefficient is positive, it ends up on the right. If the leading coefficient is negative, it ends down on the right. Now this is an odd degree function, correct? Because it's degree 1. Do you see this? Linear or degree 1. And how do we know it's a degree 1? Because the exponent on our x, the largest exponent, is a 1. Okay? Odd degree functions end in opposite directions. Do you see how the arrows are this way? Odd degree functions always do that. So arrows end in opposite directions. So leading coefficient tells you how it ends on the right. Positive, it's up on the right. Negative, it's down on the right. That's for every polynomial. And odd degree functions always end in opposite directions. All right. So this is what I'm going to give you. You're going to help me out here. It's just a separate sheet. You're not going on a separate sheet. You're just paying attention. So say if I give you this, y equals ax plus b. And I tell you a is greater than 0, b is less than 0. Say I just give that to you. And I'm going to do a really quick sketch. And that's all I'm telling you. What does this represent? The y-intercept, correct? So I have some sort of negative y-intercept. Do we agree? So somewhere down here, about there, I have a y-intercept that's negative. Could I pick anywhere down from 0 below? Yes, I can pick anywhere. What does this tell me? Nope. My leading coefficient. Is my leading coefficient positive or negative? A is, if it's open to the variable, it means? Yeah, greater. So A is greater than 0. So A is positive. If A is positive, I end up on the right, correct? And it's an odd degree. So where do I end on the left? I end up on the right. It's an odd degree, so where do I end on the left? Where do I end on the left? Down. If I end up on the right, I'm going to end down on the left because the arrows are in opposite directions, correct? So the degree tells you if you end up or down on the left. The leading coefficient tells you how you end on the right. So if I give you this, y equals ax plus b, and I say a is less than 0, b is less than 0. What does b is less than 0 mean? What does that mean?
Negative.
I have a negative what?
Y.
Yeah, y-intercept, so somewhere down here, I'm going to put it here. Is this positive or negative?
Negative.
Negative, so my leading coefficient is negative, so I know I end down on the right, correct? because it's negative, which means I do 1 on the left. Go up, because it's linear. It has to go in the same direction, right? Okay. This is what I'm going to give you. I'm going to give you 3 graphs, and you're going to tell me these 3 graphs are reliant on y equals ax plus b. I want you to tell me if my a is greater than or less than 0, or if my b is greater than or less than 0 off these each of these graphs separately. So this is my first graph. This is my second graph. This is my third. I want you to tell me if my a is greater than 0 or less than 0 for this one, b is greater than 0, less than 0 for this one, and for each of them. Go. Merrick.
Yep.
That was just random because he usually actually does work. So it's not. It was not based on people who know.
A is less than 0.
Why?
Because this.
Because what of the graph tells you that? How it ends on the.
How it ends on the right.
How it ends on the right. Okay. Kalea. B.
A is greater than 0.
No, sorry. I want to know what the B is. This B is.
Okay, it's greater than 0.
Yeah. Because why?
Because it's
Yeah. I just picked the 2 people who always have this stuff done. Just so you know, I feel bad when I pick people who don't know what's in. Okay, I'm randomly picking. Oh, it's Ethan. My just landed there. All right. A is what?
greater than 0.
Yeah. Why?
Because it's
Up on the right, yeah. And then B is what?
so cute.
Your y-intercept, positive or negative?
Negative.
Y-intercept.
It's fine.
Is it positive or negative?
Positive.
Yeah. So it's greater than 0. Okay, Ethan. Do it again because you know what you're doing. A is what?
Less than 0.
Yeah, it's down on the right. And my y-intercept, B is what?
Negative.
Yeah, less than 0. I think you were looking at C and not B. When you were answering, you gave the answers to C and not B. So I was like, let's just go to this one. I think that's when you were answering. All right. You were totally answering C.
Right here.
That's what I mean. You were answering C. That's why I was like, let's go to the one that you were giving me the answers to. Okay, here. Look at this. Degree 3. No. Ava.
Oh.
Degree 3. Why do you think this would be called a degree 3 function?
Like, hold on. Oh, because there's like, there's 3, like, terms? No, there's 4, but,
The largest exponent is a?
3.
Yeah.
Oh, so that would be the leading coefficient.
Yeah, and that's what tells you what the degree is. So the largest exponent is the degree.
Wait, so what's the difference between like 3 and 1 and 3?
The graph looks totally different. You haven't seen a cubic yet. We've never given you one.
The cubic one, like.
Yes.
So will it tell you, or will we really have to like?
You will see it by the equation with a 3. Right? That's
So
right.
you look at the exponent as
Yeah,
well,
largest exponent.
and that'll. So in a degree 1, the exponent would not be.
The largest exponent is 1.
Oh.
Yeah.
Oh, the largest exponent.
Yeah. Got it. Okay. So cubic functions, the largest exponent is 3. Turn around. Now, I'm going to give you this type of graph. Ready?
Yeah. You ready? Oh my god.
Oh, I remember these.
You don't. You never learned them before.
Oh, like I remember like seeing lines.
Seeing lines. I've seen lines before too. They're crazy. It's lines with angles and things and such. All right. So cubics can look like that. Or cubics can look like this. So, paying attention. This one has a max, and this one has a min. So it has two turning points. Does the second one have a max or a min at all? No. It has this little curvy thing here. See that little curvy thing? That's called a point of inflection. It's called a point of inflection. Now a turning point, the definition of a turning point is a max or a min. Is that a max or a min? No. So degree threes can have two turning points or zero turning points. Now, unless I give you an equation, I can ask you for the sign of the leading coefficient, even if I don't give you the actual equation. What's the sign of this one's leading coefficient? Positive or negative?
Positive.
Why? That's right, but why?
I just looked up and
How it ends on the? Would the left be positive? How it ends on the right side. And it is up. We just wrote this at the very top of the page. The leading coefficient sign tells you how it ends on the right-hand side. So if it's up, it's positive. What is the sign of the leading coefficient of this one? Guys, gotta stop. Negative, because it's down on the right. Oops. All right. My y-intercept. Is it positive or negative for this one? It's a positive y-intercept, correct?
Yes.
Now, I could say, okay, it's 2. So then my y-intercept would be 0, 2. Or they could say my y-intercept is greater than 0, right? So we can go through by actually giving a number, or by, in this case, which letter is my y-intercept? A, B, C, or D? Look at the equation. A, B, C, or D? D. Because the constant, if there's no brackets, this is always my y-intercept in every single equation, if there's no brackets. So the y-intercept of this equation is 0, D. What's the y-intercept of this one? It's negative. You could say it's negative 6. Then it would be 0, negative 6. Now, how many x-intercepts does this one have? How many x-intercepts does this one have? 3. How many x-intercepts does that one have?
1.
Degree 3 graphs. Number of x-intercepts. What's the lowest number of x-intercepts a degree 3 graph can have? Lowest, smallest is 1. Because it discos with a little bit of hoo-ha, like a little bit of woo-wah in the middle, but it still discos, correct? So if it discos, because it's an odd degree, arrows are in opposite directions. Because it does that, it has to cross through at least once. We agree? It can't not cross through, because at some point that arrow is going to have to go through if one's going up and one's going down. So the minimum number it has is 1. What's the maximum number of x-intercepts a degree 3 can have? Nope. Degree 3. 3. So the maximum is to the degree. The degree tells you the maximum number of x-intercepts. And then we can always have every other variance in between. So we could also have 2. How would 2 happen? Well, you'd have to like go through and then bounce and back up. So that's how you would get 2. But it'd still be cubic. So you can get 1, 2, or 3 number of x-intercepts. What's the domain and range if ultimately it's this going in the end? XER, YER. So your arrows are going up and down for life, right and left for life. Okay, we're on to the next page, to the bottom of the next page. No. We're going to do that when I give you an actual equation. Going to the bottom of this page. I want you to sketch the graph of the following equations given the particular values and state the domain and range. So I want you to do A, B, C, and D. I will show you A for an example. Okay? A, B, C, and D. So this is what type of graph? Linear and degree 1. So I know it's a line. It's going to be straight line either this way or straight line this way, right? Because it's linear. We did in grade 10. Okay? What does this tell me? This is my leading coefficient, correct? So it tells me how it ends on the right, correct? So this would be up on the right. And because it's a degree 1, it's down on the left because it has to disco. We agree? What does this give me? Yeah. The y-intercept. So all I know is that I have a positive y-intercept. So I just want a quick sketch. I don't know why that didn't just connect the whole thing, but okay. I want a positive y-intercept, so somewhere up here. And it's up on the right, down on the left. Do we agree? So it could be very vertical. It could be like this. Up on the right. Up on the right. And then you just have to follow it straight down. Down on the left. It could be like this. Could it not? Is that still up on the right, down on the left, positive y-intercept? Could it be like this? Still up on the right, down on the left. Any of those, right? So yours are going to all be a little bit different. The key thing is it has to be up on the right, down on the left, positive y-intercept. Okay? You're doing B, C, and D. Go. Okay. So this one means down on right, and this means, thanks, that's what that means, positive y-intercept. So I know I need a positive y-intercept, and I need to be down on the right, up on the left, so something like that. Okay, this one I need up on right, negative y-intercept. So something like that. And then this one, I need down on right, negative y-intercept. Something like that. Okay, flipping ahead. This one. I want you to try these ones. These ones are cubics. Remember, the easiest way if you get a choice to draw a cubic is it has to be symmetrically looking. So like up, then back down, then back up. It has to be symmetrical. I don't want to see stuff like this.
No, it didn't. I'll flip to it right now. No, it didn't.
So symmetrical looking. Or even like this. You could even do the cubic like this. Symmetrical looking. So if I did this first one, it needs to be up on right, positive y-intercept. So positive y-intercept, so somewhere here, let's say. So it has to be up on right, so down on left. So I could go through it like, oh my gosh, guys. I make it like symmetrical. Do like that, if you'd like. So try JKL. So here it is, down on the right, positive y-intercept. So it can be down on the right, so up on the left, so it could be anything like this. Pretend that's the y-intercept, I didn't even go where I put it. Cool. This one is up on the right, negative y-intercept. So I could be down on the left, do something like this. And then this one is down on the right and negative y-intercept. So anything like that. If you want me to check yours, I can.